Hi, what I have here on the bench today is a 200 watts BK Precision 1696 programmable switching power supply. It is rated for an output voltage of between 1 and 20 volts and a current range of 0 to 10 amps. In the same series, you can also find the 1697, which is a 1 to 40 volts, 0 to 5 amp version, and the 1698, which is a 1 to 60 volts, 0 to 3.3 amps version. These power supplies are still active models, and the new ones do not come in cheap. I think the cheapest one you can find is close to $300 in retail price. Anyway, and you might have noticed, the one I have here has a smashed LCD screen. I just got this very cheaply from eBay about a week ago, and the seller mentioned that the power supply was accidentally dropped, and thus the LCD screen was broken. So indeed, besides the broken LCD, you can also see that there are some cracks near the front panel terminals, and it has been glued back, so presumably somebody still wanted to continue using it, so it was glued back. So I knew what I was getting, and my plan was to ideally just replace the LCD if I could find one. But these LCDs were specifically made for these particular power supplies, so I wouldn't count on being able to get one unless it's from a similar donor unit. I did send an email to BK Precision's technical and customer support asking whether I could purchase a replacement LCD from them. Well, their automated email reply says they respond within 48 hours. I have not heard from them for about a week. So the alternative is to reverse engineer the controls to the LCD and put a totally different LCD in there with the corresponding supporting circuitry. So that's something I might do in the near future. But upon some preliminary power on testing, I think this power supply might have slightly more issues than just the LCD itself. For example, when I power this on, hold on, let me just power it down. For example, when I power it on, now I'm going to enable the output, and I'm going to try to adjust the voltage to its maximum. And you can probably read this one digit here as this part is still legible. It's something about 11. So basically what happens is that the output voltage cannot go much higher than that. And you can see my IM basically keep rotating this. But if I go down, you do see that thing, the voltage would start dropping. So basically it's somehow capped just around 10 volts, and it depends on the time of the day, it actually changes. So this is actually not something that is controlled by the overvoltage protection, as I do have a RS-232 cable and I connected to the computer, verified that. Also, you can see, if I just measure this, the output is not stable at all. So let me show you. So now it's 1122, so I'm actually not touching it, so now it's dropping. And right now it's only doing the 1 millivolt range, but sometimes it's actually going pretty wild, going as high as 20 millivolts. So I'm not sure what the deal is there. Let's turn it off and try starting again to see if we can see that. So I'm going to turn it off and turn it back on and enable the output. So now it's not doing that, but it clearly was doing that before, and yeah, now you can see it's actually changing to 220 millivolts instead of, now it's 23. So if you hook this on to the multimeter long enough, you're going to see that the voltage start jumping quite a bit. So I'm not really sure what's going on there, but clearly that's not something that I wanted to deal with today. And for today's video, we're just gonna open this up and see what we find inside. So I'll definitely do another video once I figure out what I need to do for the LCD, and also once I find out what is going on with the power supply, and I might do a video for fixing it and replacing the LCD. But for now, I'm just going to open it up and take a look. And it's a good idea to use a container. So I'm just going to use this tin can to put that in because there are going to be a lot of screws. And now with all the screw removed, we should be able to just open up the top. So let me just do that. And I just open it up. From the first glance, you can see that this is just a pretty standard switching power supply portion. And I don't see any controlling circuitry except for this riser board I can't see from this angle. But I suspect, just given the number of cables going in through the front panel, there may be some controlling signal coming out from the front panel. So I'm going to further remove the front panel first and to see if we can have a deeper look. So for that I need to turn this over. And okay, so it seems that there are 3 screws here. Oh, it just popped right open. Okay, so let's see. I think I should be able to remove this, shall we? Alright, so let's remove. It seems that somebody might have got in here before, as you can see here, or it's just some kind of manufacturing process, but there are some markers mark these connectors. Actually, that's a very good practice because you don't want to, especially the connectors are similar, you don't want to later on forget which one is where. So people just mark them in this kind of pairs so you know that you can put them back. So that's actually good, but I'm not sure if that's somebody did something or it's just when they're doing the manufacturing. Rather. So let's, should I unplug this? Okay, so let's first remove this ferrite bead. And this should just be clipped on. Okay. The reason is that this is a switching power supply, so there are a lot of digital noise. So they wanted to make sure that the digital noise is sufficiently clamped. So, oh, this side is glued on, I see. I just might remove this. Hang on. I should be able to pull this up. It's a little bit awkward. Okay, so now this is off, so I can put this through. Okay, so it's not as easy. So there are more connectors. So, you know, let me just unplug all these. Because these are just the output connectors. I can easily put them back. And if I can unplug these at all. Okay. So there's another toroid to clamp the noise for the output. But right now, I think, if I'm not breaking this, I can take this out somehow. It should just be, yeah, here we go. So now, what I'm going to do is I'm going to, I don't want to lose any screws here. I'm going to feed this back through the opening. So we should have a much better look at what is going on here. Alright. So I'm not quite impressed already by the construction. I mean, these openings, you can see, is quite sharp. Even though they do have this plastic piece out here, and you can still cut through the wires. So that is something, I don't know. Okay, should I just unplug this cable? Yes, let's do that. Oh, what is it? Alright, so let's just unplug all the cables here. So this one feeds through. And okay, so we still have a grounding wire right here. I'm not going to worry about that right now. We can already see what is in here. And from the first glance, I actually am very shocked at how this is done. Let me zoom in and I'll show you what I saw. So you see these connectors. They're soldered directly to the output, but the soldering quality is actually quite poor. And let me see here. And if you notice that these are just, it looks almost as if they didn't have a soldering iron that is powerful enough. So they put the wire here and, didn't have enough time to melt all the solder and just, somehow slapped it on. But it could also be that somebody did some modification or servicing this unit and did something in between. You can't really tell. But that said, I don't think that was the case, because even if you look at this regulator, you see how this regulator tab was soldered onto the board, and just a glob of solder here. So the job they did here is actually quite poor. And for example, this really looks, instead of it like a $300 power supply, it looks like something much cheaper. And instead of a proper connectors, they just have something like hot glued on here. So it looks like a lot of the cheaper products. And instead of the proper ribbon cables, these cables are again those cheap connector cables. So anyway, so let's take a look at what we have on this board. Actually, I wanted to take this board apart even further. Now I'm really curious to see what is on the other side, especially we have that broken LCD. So let me do that. And I think that's the last one. And to get this further out, I think I might... Okay, so these are actually good. So this front side, the terminals are on a separate board. I was worried that I need to remove these first, but it seems that I just need to remove this rotary encoder cap. So it came right off here. So now this whole front panel assembly should just come right off. And indeed. Okay, that's a little bit disappointing. There's nothing on this side. So you can clearly see that here's our smashed LCD, and I don't see a clear part number. There's some writings here. I will write that down, but I don't think these are any these are part numbers. These are just probably some manufacturing data or some specific proprietary markings. And by the look of it, this is just a parallel LCD, and it has, I think they are, let me just see the bottom here, there are 28 pins on either side, so there are altogether 56 pins. So again, finding a replacement LCD, as I mentioned earlier, is going to be quite tricky. And I may, at the end of the day, just reverse engineer the protocol and replace one myself. But that looks like it's doable. So let's take a look at what we have on this board, shall we? So the first thing is that I noticed the LCD driver used here, and not sure if you can read from that angle, but here I can see this is NJU6433. So this is actually just a standard LCD driver, and the control logic is using I2C. So I think later on, not in this video, but some other time, I'm going to tap into this LCD to see what control signal looks like. So in theory, we should be able to bypass this driver. Instead of driving this parallel LCD, we could using whatever control signal and translate that into our own LCD driving. But that could be very time consuming because we simply do not know what segment corresponds to what display elements on the screen. So besides that, we also have a, this is upside down, hopefully you can read it. It is a ADU 831, let's see, BS. So that is actually an 8052 microcontroller. It is actually quite a beefy product. It has quite a few 12-bit DAC output and 12-bit ADC input. So what we can see towards the bottom of this portion is there's a MAX 485 and there's a the RS-22 transceiver. It's I think that's a MAX 202. So that's a yeah, MAX 202. So that's actually RS-22, sorry, 232 transceiver. We also have a CD4052 dual 4-channel analog multiplexer circuit here. So these are handling the communication, as this unit does support both RS-485 and RS-232. And you can see there are optocouplers. So all these lines are isolated. And just by looking at some components here, we have some op-amps. And that's pretty much it. So the logic actually is all handled in this microcontroller for driving the input, output, and that's not the output, but output control signals. And the control signals are actually going out to the digital to the analog board through these connectors. So that's pretty much all we have on this board, and yeah, so we do have a rotary encoder, and so that's pretty much it. So now let's move our concentration to the actual power supply unit. And for that, I think I also need to remove the board because it's crowded and I can't really see any some of the chips, what they are from this angle. So I will just take this board out and hopefully we can see it better. Okay, so I finally managed to push the board out. So let's take a look on this end. Oh, this is gonna get a little messy. So what I'm gonna do is I have to disconnect the mains power here. And well, this is just the grounding. Should I remove the ground? Why not? Let's remove this as well so that we can have a much, whoops, okay, hang on, I don't want to lose any of the bolts either, so let me unplug this, and this thing should come back. So this board is out, so now let me just tidy this up, and I will be right back. So now we can take a look at this power supply, switching power supply portion. And to be honest, I'm really not quite impressed by the construction this BK Precision 1696 unit has, because if you take a look at the component layout, everything is just laid out. It's not really. It looks pretty messy. You have this wire jumping across the high voltage portion of the circuit. And you also have wires just you know, kind of like dangling from here, whoops, you can't see, from here all the way to from the transformer, just in the air, and wire it directly to the board. And also it just And the board looks really cheap, and all the components, you know, it's just I don't know, for a $300 power supply, you would expect that they're using the top-notch components, but this one really is no different than a standard power supply that you get for, like, say, $40, $50, those computer power supplies. So it looks, I mean, it's okay. I suppose it does its job, but nevertheless, it's a, you know, the board is itself is not really an expensive board either. And then we have this riser board, which it surprisingly doesn't have much on it. So let's see what is here. These are, oh, just LM324, so op amps. And yeah, just a few op amps here. So these are probably controlling some of the adjustments of the voltages. Since we don't have a schematics for this, so I'm just guessing here. And you do see this line here across the power supply. So I'm not sure if you see this line. So basically it tells you that under this section it's a low voltage portion, and on the other section it's high voltage. And the dead giveaway is that you see this chunky switching power transformer that is sitting between the lines. So one side is for the primary, the other side is for the secondary, which is isolated from the other end. And also this optocoupler also isolates the primary and the secondary. So let's flip it over and see what we have at the bottom. Wow. So I am really surprised at, I'm wondering if these were actually somehow people had redone this. I don't think so, because these caps, let me just zoom in here, they do seem like it's original. And some of the bypassing caps, you know, they're like, okay, we just we don't have space, we will solder them on the reverse side, which is fine. But if you look at the traces here, I mean, I understand these are the traces that are high current capability traces, but besides the residue you see all over the place, you also see that these are not properly flowed. So this, along with the connector on the front panel that I showed you earlier, suggests that probably they were not really using you know, the proper wattage soldering iron. And because these things are clearly not flowed correctly. So now, whether or not this contributes to the problem I had, I don't know. I have to take a deeper look. But clearly, this does not instill any confidence, especially for a lab-grade power supply. And in fact, I have not seen something built this bad for a long, long time. Not even from, you know, some of the no brand name Chinese products. And as a BK Precision product, this certainly should not be the case. So I'm not sure if this is just the unit I got, but I don't think so, because you can see, even if it is somebody touching things off, you cannot, you know, it's all over the place, the same issue that you see here. It's certainly not just limited to the bottom, because as you can see here, even on this riser board here, you can see we just have a cap right here, and we have some you know, resistor. Okay, so they're good, nice enough to put a tubing on the one leg, because it might be shorting some other components. But you can see here we have just a wire hanging directly from the board to some other places, and worse yet, if you see this this red wire here, we are just hanging it off the. This is just soldered directly from the jumper wire to one of the component pad on the other side. So the construction is really, really poor, and if I were BK Precision, I would be looking into, if they contracted this to some other third party, I would certainly raise a concern there, because this could easily tarnish their brand name, especially when the components start failing. And just from my casual look through, and I didn't see any bulging capacitors, any obvious places that could have gone wrong. But nevertheless, as I mentioned earlier, we did have some issue with the switching power supply portion, and we certainly could take a look later, but I don't think that would be for today's video. And let's just take a quick look at what is on this board, shall we? So we have this power coming in from this end, and we have some common mode choke and filtering going on here, and we goes through this bridge rectifier, and coming out as a DC voltage somewhere in the 150 volts range. And if you notice, you have two transformers here. Actually, the reason is that this one here, this circuitry, you can't read this chip number, but I can tell you this is a MC33262, which is a power factor controller. So this portion of the circuitry must be for power factor correction. So to make this whole switching power supply to the pure resistive power factor of 1. So that's what this side of the circuit is doing. And the actual switching power supply portion comes on this end. So now all the caps are actually no brand name caps. So the caps used here, if we can just see this is caps on, and I think I heard those before, but not sure if who manufactured those. And these are actually 85 degrees rated caps. So usually in a switching power supply, these are usually 105 degrees rated. So could it be that some of the caps started failing? I don't know until I taking those out, but certainly that's one of the first things I'm going to be looking at. As power supplies like the switching power supply, sometimes the output became unstable because the because of the caps started drying up. Again, we have these lower voltage 35 volts caps here for the output filtering. So I don't think these caps are going to play as a major role as the input caps, but nevertheless, I will have to take a look. And by the fact that when I power this on, it does output some voltage, and also the primary control is somewhat working, that suggests that probably there's no failing active components like your MOSFETs or your transistors, and all the ICs are presumably still functioning correctly, because otherwise you won't even get any voltage at all. And certainly the digital board is working properly because we have a RS-232 communication to the computer, and everything there is working properly as well. So that's pretty much what you have here for the BK Precision 1696 power supply. And actually, when I did take this further apart, and the construction is really poor. Even manufactures itself in the front panel here, and if we can focus here, sorry, the back panel here. So these, for example, the wires connecting to the 485 port, it's just soldered on rather poorly. And then we have this crimp terminal, and you can see we have a cap soldered directly on the between the pins on the power supply. So this is your on the power supply input. And surprisingly though, this fan, if you look at it, is really clean. I do know that this one actually has a temperature controlled fan. So either it's during use that the power level never reached the level that they need to turn on the fan, or this unit simply just hasn't been used that often. And probably the latter is the case, because the inside is really clean. So I assume that it's some kind of they dropped the unit and then it became broken. Nobody cared to fix it. And here again, you can take a look at this. Now I took this board out, so you can see this more clearly now. You see this two suppression caps here, and there's one cap, is the output filtering cap, tucked underneath there. And you can see how poor this soldering job is. And this is your ground wire here. I hope you enjoyed the video and learned something new. And if you liked the video, please give it a big thumbs up, and that definitely helps a lot. And I will catch up with you next time.